The solution is Rankine cycle. So we use Rankine cycle as the ideal cycle for vapor power cycles. So we call it vapor power cycles because the working fluid is vapor. The working fluid can be in the state of vapor or can be in state of the liquid during the operation in the cycle. So we call it vapor power cycles. And in these cycles, the working fluid is normally water. Okay, so let's analyze the ideal cycle for vapor power cycle, which is the Rankine cycle. Let's look at the operation. On the figure, you see the operation of this cycle. There is a turbine, a condenser, a pump, and a boiler. And let's look at the operation on TS diagram. Process 1-2 is, which is the pumping of the water. Process 1-2. We assume it is an isentropic compression process in the pump. So process 1-2 is isentropic, entropy is constant. Process 1-2. And a pump is different from a compressor in that it only handles liquids. So the water is in the liquid state as it flows through the pump. So the water enters the pump at low pressure. It leaves the pump at high pressure, which is the boiling pressure. So at 2, liquid water enters the boiler. 2, it is heated in the boiler until it reaches the saturated liquid state, because state 1 is saturated liquid, state 2 is compressed liquid. And as you heat at constant pressure in the boiler, the process is constant pressure. It reaches the saturated liquid point first. Then as you transfer more heat in the boiler, then it vaporizes at constant pressure until it becomes saturated vapor. You transfer more heat and it leaves the boiler at superheated vapor state. So state 3 is superheated vapor. So the water is steam at high pressure and temperature at state 3. And in the boiler, here we consider the process as the constant pressure heat input. In reality, we know that in the boiler, there is a fluid being burned with air, and the heat of the combustion gases is transferred to the water. That's actually what's happening. But we don't have to worry about these details in the cycle analysis here. We just consider heat addition at constant pressure. So at 3, it enters the turbine. And the turbine expansion process of steam is considered as isentropic. So process 3-4 is isentropic expansion. And high pressure, high temperature steam does work against the turbine blades. And as a result, turbine blades rotates the shaft. And there is work output from the turbine. So at the exit of the turbine, we have steam with some amount of moisture, as you can see at state 4. State 4 is a saturated liquid vapor mixture with a high vapor fraction, with a low moisture fraction. And then at 4, this steam enters a condenser where heat is rejected at constant pressure to a low temperature medium. In reality, use a lake water or atmospheric air for the cooling medium in the condenser. If you use a lake water, for example, lake water enters through this condenser, which is a heat exchanger, and heat is transferred from the steam to the lake water. And the steam condenses here in the condenser at constant temperature and pressure until it leaves the condenser ideally at saturated liquid state. And this completes the cycle operation. So in order to summarize, it is easy to see that process 1-2 is isentropic compression in a pump, 2-3 constant pressure heat addition in a boiler, 3-4 isentropic expansion in a turbine, and 4-1 is constant pressure heat rejection in a condenser. And this ideal Rankine cycle, this is the ideal cycle. The compression and expansion processes are isentropic. There are no pressure drops. So this cycle is internally reversible. Internally reversible cycle. Because heat addition is taking place across a finite temperature difference, we know that it's not externally reversible. Okay. Let's look at the analysis of this cycle. How do we analyze this cycle? How do we analyze this cycle? Okay, let me write the equations, thermodynamic equations for this cycle. Okay, so let me show it here. Let me show it here. Let's look at the pump, the process 1, 2, process 1, 2. It is the pumping operation between 1 and 2. The work input for this process is equal to H2 minus H1, enthalpy at state 2 minus enthalpy at state 1. So, how did we obtain this? From an energy balance on the pump. If you write an energy balance on the pump on a unit mass basis, there is energy entering by mass per unit mass, which is H1. There is energy entering by work, which is work pump. Okay, work in by the pump, and energy leaving by mass, which is H2 per unit mass. And from here, if you solve for work input to the pump, it is H2 minus H1. But when we analyze work input to the pump, we don't know H2 normally. It is difficult to determine H2. H1 is easy to determine because the inlet state to the pump is considered as saturated liquid, as you can see in TS diagram. But we don't know H2. So an easy way of determining work input to the pump is remembering that this operation is isentropic. We can use this relation V1 2 minus V1. So because the working fluid is liquid throughout the pump as it flows through the pump, the work input during the isentropic case can be determined from specific volume, which is almost constant through the pump because it is a liquid, times pressure at 2 minus pressure at 1. So this is how we determine isentropic work input for the pump. And after we determine work input, we can determine H2 from H1 plus work input. Okay, this is how we analyze the pump. Let's analyze the boiler. It is process 1, 2 is the pump operation. Now process 2, 3, which is the boiler operation. For this operation, again, we write an energy balance on the boiler per unit mass basis, and the result would be this: Qin is equal to H3 minus H2. Of course, when we write this energy balance equations, we neglect kinetic and potential energy changes, which are a good approximations. This is the heat input to the pump, to the boiler, H3 minus H2. Next is process 3, 4, which is the turbine operation, and W out from the turbine is equal to H3 minus H4. Enthalpy at 3 minus enthalpy at 4, state 4. And then finally, for process 4, 1, the Q out, the heat rejection, is equal to H4 minus H1. H4 minus H1. Now, we have all these relations to determine work input, work output, heat input, and heat output. How do you find net work output? The net work output is equal to work out from the turbine minus work in to the pump. If you consider the entire cycle as a closed system, and if you apply an energy balance, you can easily see that for the cycle, Q in plus W in is equal to Q out plus W out. For the entire cycle, you will obtain that. And from here, Q in minus Q out is equal to W out minus W in. So net heat input minus heat output is equal to work output minus work input. That means the net work output can also be written as heat input minus heat output. We also manage that. Now let's express the thermal efficiency. What is the thermal efficiency of this cycle? Thermal efficiency for any heat engine is given by W net over heat input. And what is W net? You can write as work out minus work in, or Q in minus Q out divided by. So we write it like this: Q in minus Q out divided by Q in, which is equal to 1 minus Q out over Q in. So this is the thermal efficiency of this Rankine cycle. So this completes the analysis for this cycle.